Hello guys, now we go for the construction of dual forms for convex problems. Consider we've got the primal form of the support vector machine optimization problem, as we've seen before. How can we get the dual form? I think you guys remember, but let's just remember it before going into the details of how to solve it, how to solve those problems using interior point methods, as I mentioned at the end of the previous video. So at first I need to build the Lagrangian function. The Lagrangian, in this case, it's a minimization, remember? I can write it as half of this optimization function. I'm using minus here, but if this is a minimization, I could use plus, okay? But I'm going to use the same model I've been using with you guys, so I'm not change this actually, but I could. It would like make actually it would make some change in terms of the convex cone, as we discussed like some videos before. But at this point, I think it's not necessary to discuss on this. Okay, so I have my constraints. Of course, I have to make those equal to 0. So I bring this one, of course, to the left side. And I multiply all this by some Kentucky multiplier, which is my alpha I. Of course, if I have like m, as you can see here, constraints, I have m Kentucky multipliers, and my sum would be from 1 to m. I could just open up and have the first, second, third, but it's of course easier to just show this using a sum. On top of this, I need to differentiate my Lagrangian function in terms of my variables, in terms of w and b, most especially. If I differentiate in terms of w, we've got, of course, in this case, it's going to be 2 multiplied by, that's the same as w. Okay. And differentiating in terms of this, and all this in terms of w, of course, you have alpha multiplied by y multiplied by x, all of those index in terms of alpha for 1 to n. That's here. Of course, my w is equals this sum, as you can see. Okay. So on top of this, what I have is, of course, I can differentiate in terms of b. Differentiate in terms of b was multiplied by y. It was multiplied by alpha, so it's going to be minus the sum of alpha y's equals 0. All those equal 0 to make the gradients parallel. At this point, I think you guys remember. We are trying to make the gradient vector of my position objective function parallel to the gradients of my constraints, all of those constraints combined. Actually, now at this point, probably you noticed, these will form a basis in my space. And then I'll have Lagrange multipliers, or Kentucky actually, in this case, multipliers, composing be multiplied by my basis, by each vector, of course, the gradient vectors for my objective, the gradient of my objective. So of course, this point here. Okay. So now we can just give another step, which is the distribution of alpha I. This is going to be alpha I, yi in terms of my dot product, and alpha I, which is here, of course, and minus b, because of this minus b times alpha and y, as shown here. This minus with this is going to be plus the sum of alphas, as shown here. Of course, because of my differentiation, I can substitute this term and make it equal to 0 over here. And of course, this is going to be part of my constraints, because everything that's vanished from my Lagrangian must be kept in my dual form. I think you guys remember that. And then we're going to have, of course, this form, just canceling out this. and substituting my W by what I found from a differentiation, and all those substitutions are just a way of finding a dual form using Lagrange for my original problem. Okay, so applying this W over here, this is the same as the internally of this norm, that's the same as the dot product of this W by itself. Here is just W. So I can open up this, and that's going to be the same. Of course, these two can cancel out the square root, which is being applied here. And here we have just the dot product, as you can see over here. Okay? Dot product of W by W itself. Here I have W over here too. And then, given those operations inside, given this, dot product is a linear transformation, can just bring this sum and the scalars outside dot product. The same happens here, can bring alphas and y's outside of my dot product. Of course, I have this sum of alphas at the end. Doing those simplifications, I have this second form you can see here, sum alpha I alpha j, yj. Of course, i's vary in terms of one of those sums and j's in terms of the other, and inside the dot product. Here, of course, minus and minus the same with the same big picture, yeah, alphas and y's and dot product plus alpha I. Of course, here I have like half something, and here I have -1 of something, so I can just, of course, make the subtraction, and at the end I have -half this plus the sum of alpha. This is my dual problem. I think you guys remember. You can see it's a maximization. Now, just in terms of alphas, I need to find the alphas, which are, just to remember, are my Cauchy-Tucker multipliers, which are multiplied by the gradients of my constraints, which I expect to form a convex cone in order to make it equal to my objective function. So this is my maximization. Of course, my Cauchy-Tucker multipliers have to be greater than or equal to 0 for all my constraints. I think you guys remember. And this is the result of my differentiation, which was vanished in my substitution to find my dual form. Yeah, that's pretty much everything. At this point, I have the dual of my support vector machine problem. And why that's important, I want to explain to you at this point that something has to happen with this objective function. This part over here must be concave. If it does not form a concave function, of course, take a look, it's going to be a negative. A negative convexity is a concave function. So while in my primal problem I had like something to the square which was positive, forming a convex function, now I have something that's negative in terms of something that I expect this to be something like minus x squared. And this minus x squared, of course, is going to be a concave function. It's the same, just to show you guys the plot. In my primal problem, I expect to have something like x squared plus y squared. I expect to have something like this, which is a convex function. Okay. In my dual problem, I expect to have concave function, which has like negative signs over here. Take a look what's going to happen with my plot. So if in my primal problem, again, primal is here, I look for some minimum. My dual, I'm going to look for some maximum. What's going to happen that's really, really nice is exactly this. Let me plot both for you, just to have like some picture, some big picture. Right, what I expect is exactly this. Those two convex and concave functions will touch at this point. So the point that they touch is like this. They touch at this point. While I'm solving from the primal problem, I try to find some minimum. And if I solve the problem using dual form, I have the maximum. And of course, they will provide the same solution because the minimum and maximum will touch themselves, okay? Providing the same solution. That's of course a way of seeing, because this primal problem will be in a given space of variables, and this dual problem in another space, completely different space of variables. But it's nice to see like this because I think it makes easier to understand how they kind of touch each other. Of course, they are going to touch, really touch, if I make like some conversions in my function. That's possible. I'm not interested in doing that at this point, but that's really possible. Okay, so we're going to see later that we have a way of guaranteeing that this term forms some concave. Because when you look at this, you are just seeing a dot product of xi and xj. How can you be sure that this multiplied by alphas and y's is going to be concave? We have a way of knowing that this is going to be concave, but we are going to discuss that later. It's nice to tell you that if this guy, if one of those alphas is negative, and that's why they must be positive over, take a look for the Cauchy-Kontucker condition. Just consider one of those is negative. What's going to happen with this sign? It's going to change. Is it going to be convex? It's going to be concave? No, it's not going to be concave anymore because it's going to change my sign. That's something to think about. Just like take some time, imagine what's going to happen if one of those alphas, just one of those, like I have m, but just one of those is negative. What's going to happen with it? Just imagine that, okay? This is the kind of concave function we expect from our dual problem, okay? That's why we try to maximize, and now it makes sense why we are maximizing. We're trying to reach this point on top over here. Guys, I hope you understood all those steps, and then we go for the next video. See you.